Okay. So yeah, I mean, there's not too many people here, but maybe I can say about Srijita. I mean, I don't know what there's. I don't know how to introduce her really, but she's been doing a lot of very interesting work in complexity, quantum complexity, and this is one of her recent results, one of her many results actually. Uh, and yeah, so let's hear from Srijita.
Yeah, yeah. Thanks for the introduction. So yeah, the title of the talk is a little bit different from the archive version. Yeah. So this is joint work with Rohit Chatterjee and Srijita Kundu. And okay, let's start. So okay, the no cloning theorem is one of the most well-known features of quantum mechanics. So this was discovered by Reuters and Zurek in 1982, or explicitly written down by them at least. And it says that given an unknown quantum state, there is no quantum operation that takes the state to two copies of it. So, and this is just because the mapping from psi to psi tensor psi is nonlinear. So this is just an impossibility statement, but more useful results are what is the average fidelity you can achieve for cloning. So Werner showed in '98 that if you have high random states, then for any cloning operation, the average cloning probability of producing say k+1 copies given k copies is exponentially small if k is only polynomial in the number of qubits. So this is only for hard random states which are continuous, but finite ensembles of states can also be unclonable. Some good examples are these things called binary phase states, which are like you take a random Boolean function and you take a superposition over all its inputs and put the sign of fx as the phase of x. Also, these things called Wiesner states, which are used for quantum money and such. So all these results are information theoretic. So these are without any assumptions on the computational power of the clone or of whatever the cloning operation is. So this
unclonable property. There's a question. So there's a question. Is it okay to interrupt you while you're? Or do you prefer to have this question?
The previous slide. Hello. In the previous slide, the second point, average cloning probability of producing k+1 copies. Like, I didn't quite get the point. Like, could you once briefly explain that? So, what are we given over there?
You're given k+1 copies of k copies of an n-qubit high random state, and you're asked to produce k copies. And give for any CPTP map or whatever that you can apply to the k copies, you want to measure the average fidelity with k+1 copies. And yeah, if you take the average over states, it's this number.
Okay. Hi. So when you say average cloning probability, are you talking about average? Is it about the fidelity of cloning or its probabilistic
fidelity
of? Okay.
Yeah.
Thank you.
Okay, I'll resume. Okay, so this unclonability property is something that separates classical information from quantum information, because classical information is always trivially clonable, and this property is very useful in cryptography. So in particular, many novel cryptographic tasks that are completely impossible classically are possible quantumly due to unclonability. So examples of this are unforgeable quantum money, which was proposed by Wiesner even before the no cloning theorem was written down. Actually, then there were subsequent developments by Aaronson and Cristiano, Zhandry, etc. Too many to list. So there are also some primitives like unclonable encryption and decryption, things like quantum copy protection, and so on. Quantum also secure software leasing, blah, blah, blah. So the question we ask in this paper is, so we've seen that this unclonable property of quantum states is useful in cryptography. we ask in this paper, is this unclonability property also useful for computation? What I mean by that is, are there problems that can only be solved using unclonable quantum states? A natural work can to ask this question of quantum states are quantum proof and advice states, because those are things that are sort of given to us like externally in computation, rather than asking something like, does an unclonable quantum state rise in the middle of a quantum circuit or something? It's natural to ask this with quantum proof or advice states. So our results are as follows. All of these things will become more clear later as I define some of the concepts later. But roughly speaking, at this point, our first result is that with respect to a quantum oracle, and I'll explain what a quantum oracle is later, there exists a decision problem that can be solved by a quantum polynomial algorithm only using an unclonable quantum state as proof with respect to the quantum oracle. And our second result is the same as the first, except with quantum advice. So with respect to a quantum oracle, there exists a decision problem that can only be solved by a polynomial-time quantum algorithm using an unclonable quantum state as advice. And our third result.
Yeah. Sorry to interrupt you. So when you say unclonable quantum states, is it not that all arbitrary unknown quantum states are not clonable? So why we use this term unclonable quantum states? Is there any clonable quantum states that you also refer to?
Yeah, I mean, so if you're promised that your state is always on the computational basis, then
that means you know the state in that case. If you know the state, then it is obviously clonable. But if you are an arbitrary quantum state, then it is then you cannot unclone, as you have mentioned in the no cloning theorem, right?
Yeah. Yeah. So I'll when I get to the definition a bit more in detail, it will become clearer.
It depends on the family you're thinking. The family of states, but she'll explain it. I just wanted to say quickly, maybe other people are not actually all that familiar with proofs and advice.
Yeah, I'll explain what they are later.
Want to say? Okay. Thank you.
Yeah. So let me just state the third result, then I'll start explaining what proofs and advice are. So the third result is that there is a relational problem, so not a decision problem in this case, that can only be solved exactly by a quantum polynomial-time algorithm, only using unclonable quantum states as advice. So this result is not with respect to an oracle, but it's for relational problems instead of decision problems, and now it's also for exact quantum computation instead of bounded error as with the first two results. Okay, so yeah, so now I'll explain what quantum proofs and advice are. So
sorry. Before we move on, just a quick question about the result. Is there like any inherent barrier to proving the first result unconditionally, the decision result, the first two results, or like there's something?
Yes, there is.
Okay. Which I guess you'll explain later. Okay, so I'll wait.
Yeah. Okay, so quantum proofs come up in quantum generalizations of the class NP. So like the randomized generalization MA of NP, these are the quantum generalizations are placed in terms of an interactive game. Okay, not really interactive game, but a game between computationally bounded verifier Arthur, who has some input and he wants to know if it's a yes instance of a particular problem, and mysterious wizard Merlin, who's like computationally unbounded. Merlin knows X and wants to convince Arthur that X is a yes instance, regardless of whether or not X is actually a yes instance. So the requirement here is that if X is actually a yes instance, there must exist a witness. Okay, I call this witness here, but witnesses and proofs are the same thing. I should have written proof. So if X is a yes instance, then there should exist proof that Merlin can send to Arthur to convince Arthur with high probability that X is actually a yes instance. And if X is a no instance instead, then every possible proof that Merlin can send to Arthur is rejected by Arthur with high probability. So no matter what proof Merlin sends to Arthur, Arthur will not be convinced that it is a yes instance. So now how do you make this quantum? The approach that is taken in the complexity class QMA is that Arthur is now a polynomial-time quantum algorithm, and the proof that Merlin sends to Arthur is a quantum state. So depending on, so Merlin knows X, and depending on X, Merlin sends a state, quantum state psi X to Arthur. On the other hand, in the class QCMA, the approach that is taken is Arthur is still a polynomial-time quantum machine, but the proof that Merlin sends to Arthur is a classical string. So depending on X, Merlin sends some classical string px to Arthur. So so it is clear that QCMA is contained in QMA because you can also always encode a classical string as a quantum state. But it's one of the most fundamental questions whether this containment is strict, whether you can actually separate QMA and QCMA. But unfortunately, even proving an oracle separation between them is really hard. By an oracle separation, I mean all the algorithms in question have access to an oracle, which may be a classical function. If it's a classical function, it's just a string from 0 1 star to 0 1 star. Or it could also be a quantum oracle, in which case it's a sequence of black box unitaries. So all the algorithms in question can query this oracle as one time step. And so when we say oracle separation, we mean a separation in this setting. So quantum oracle separations between QMA and QCMA have been known for a while. The first one was shown by Aaronson and Kupperberg. Since then, there have been some other maybe slightly less quantum oracle separations by Buhrman and Kretschmer, for example. Yeah.
Sorry to interrupt, but when you have black box unitary access, do you also give access to the inverse of the unitary? Is that important? It doesn't matter, or?
I mean, I guess the constructions I've seen, the unitary is typically self-inverse. I guess you can give access to the inverse in general.
Because the intuition being that if you have access to like the gate description of a unitary, then you can obviously apply the inverse of the unitary as well by just running the gates. So I would imagine that it's more physically relevant to also give the inverse of the unitary, but you're saying that somehow the constructions are already self-inverse, so it doesn't really make a difference in those.
Yeah. I guess, yeah, I mean, if you wanted the most general model, you would give access to the inverse as well. Yeah.
Thank you.
So yeah, but ideally we want a classical oracle separation between the classes because so if you make the oracle quantum, you're kind of making the problem quantum in a way, and that gives quantum proofs an edge. And also there are separations that don't relativize with respect to quantum oracles, but relativize with respect to classical oracles, which we found out recently. So yeah, people have been trying to prove a classical oracle separation between these two classes. So for example, there was some recent progress in actually the last couple of years by Natarajan and Liu, Pelikanus, Yamakawa. I did something or another paper since I made the slides and I forgot to include it. So the thing is,
yeah. You made an interesting remark. You said that there are problems that you can separate that relativize relative to a quantum oracle, but not to a classical oracle. Do you remember off the top of your head what the problems are?
Yeah, I had a paper on arXiv about this last week.
Okay, I'll look it up.
It's called a cautionary note on about quantum oracles. You can look that up.
Okay, got it. Thank you.
So why do I bring up QMA versus QCMA? So what we want to show that there exist problems that can only be solved by unclonable quantum proofs. But any problem that can only be solved by unclonable quantum proofs, but must necessarily separate QMA and QCMA, because QCMA is the class such that there exists a classical proof, and classical proofs are always clonable. So yeah, any problem that only has unclonable quantum proofs must necessarily separate these two classes. Yeah, like I said. And as it turns out, we can use one of the quantum oracles that have been used to separate QMA and QCMA. In particular, we use the Aaronson and Cooper-Work quantum oracle. Okay, now I'll explain what quantum advice is. So,
sorry,
yeah.
Just to quickly make sure I'm following. So, in your previous slide, was that the justification why you were saying that you don't expect a decision problem to give an unconditional separation? Okay.
Yeah.
And are there like consequences, complexity theoretic consequences, if we are able to separate QMA from QCMA without an oracle? Like, does something crazy happen?
Nothing crazy happens, but we're not able to separate anything without oracles. So.
No, I know. Like so it doesn't separate. Like things don't collapse and stuff. Is what I was asking. Which
No.
Okay.
Yeah, I mean, we expect it to be true, but I don't think it's within our current capabilities.
Yes. Thank you.
Okay, so quantum advice. Well, we will be talking about quantum advice with respect to these two decision classes. So the class BQP by qpoly is like the decision class BQP, except with polynomial-sized quantum advice, and BQP by poly is the class of BQP problems that class of problems that can be solved with BQP algorithms with polynomial-sized classical advice. So advice is like proofs in that it is given to you by some external agent who has unbounded computational power. But unlike proofs, advice only depends on input size and not on the specific input. And also advice is always trusted. So you don't need a requirement that, for no instances, no advice should be accepted with high probability. Advice is always trusted. So you just require that there exists some advice that can help you solve the problem in yes or no. So the question of oracle separations between QMA and QCMA seems highly related to an oracle separation between BQP by qpoly and BQP by poly. In fact, basically all the constructions that separated QMA and QCMA with quantum oracles or some limited type of classical oracle also give a separation between BQP by qpoly and BQP by poly. I don't think there's a black box relation or anything between the two results, but with a related construction, you can always give the BQP by qpoly versus BQP by poly separations as well. On the other hand, so this is only with respect to oracles for decision BQP by qpoly and BQP by poly. But the relational versions of BQP by qpoly and BQP by poly can be unconditionally separated. So this was shown by Aaronson, Buhrman, and Kretschmer in 2023. So by the relational version, so these are the classes FBQP by qpoly and FBQP by poly. So this instead of a decision problem, this is just defined for polynomially bounded relations. So yeah, so for a particular string, you can have many possible outputs. The outputs are also some polynomial length string, and the outputs are like it's called a polynomially bounded relations because the output length is polynomial, and for any given input, then there can be many possible outputs. Yeah, that's why it's a relation. This Aaronson, Buhrman, and Kretschmer construction actually separates a class we'll call FEQP by qpoly and FBQP by poly. By FEQP by poly, I mean that the quantum algorithm in this is actually exact, it's zero error. So by EQP, I mean exact quantum polynomial time, basically. And so I said we'll separate the relational versions of, as in we'll show that there exists a class that can only be exactly solved by unclonable quantum advice, and we'll in fact use this Aaronson, Buhrman and Kretschmer construction.
Srijita, in your last slide, one quick question.
Yeah.
So here, do you know of any separation between QMA and QCMA that does not also imply a separation between BQP qpoly and BQP poly? Because you said that there's no black box, reduction, I guess.
It doesn't. So it doesn't imply it or anything, but usually with a related construction, you can also.
Right. Yeah. So I was wondering if you know an example for which we don't know how to go from a separation.
In our paper, we said it. A related construction probably also separates BQP by qpoly and BQP by poly, but we didn't actually prove it. If you want to count that.
I see. Thank you.
I mean, it probably works. We just didn't bother proving it.
Right. Thanks.
Hey, Srijita. So I have a couple of questions. So one is like exactly what you wanted to ask. So QMA. So I would have imagined the QMA and QCMA separation would have resulted in a separation between BQP by qpoly and BQP by poly. And you're saying that is not the case.
No. At least not in a black box. Yeah.
So the second thing is, so if you have a separation under the relational versions, it would also be true for the decision problems, right? I mean, so because functions are decision problems and functions are relations. Like, am I missing something here? So relations are generations of functions.
As in, the separation only works for a relation, it's not for a decision problem.
Okay, so there's some caveat which actually says like only for a relation which is not a function would you have a separation.
Yeah, as in it's a specific construction that specifically gives a relation and not a function.
Okay, makes sense. Thanks.
Okay. Now I'll get around to explaining what an unclonable proof or advice actually is. So the weaker notion of the existence of a family of unclonable proofs or advice have been considered in some previous works. We'll consider a stronger notion of all possible proofs or advice being unclonable. But let's examine what this weaker notion is first. So what the setup is, suppose you have some proof state, a family of proof states X for an input X. This is given to a cloner, let's say A, and the cloner knows X. And the cloner does some sort of quantum operation on psi X and distributes it between two verifiers, B and C. And both the verifiers then want to use the parts of the quantum state that was distributed to them by the cloner to determine if X is a yes instance of the problem. The setup for advice is similar, except you have some state psi n that depends on an input n, and it's given to a cloner. The cloner doesn't know an input because it's not, and the advice is not specific to an input, and the cloner distributes it between two verifiers. Now the verifiers potentially get different inputs, which are both of the same length, x1 and x2 and 0 1 to that, and they want to determine for their respective inputs if they are yes instances or not. Now we want the strongest possible notion of unclonability. So we want to say that the functionality of the state psi x in the proof case, or the functionality of the state psi n in the advice case, needs to be cloned by the cloner rather than the state itself. So what I mean by this is that the cloner could try to produce two copies of the state psi x itself, but the cloner doesn't have to do this. The cloner could do something like create some sort of entangled state phi x between B and C, such that somehow B and C are both able to use their parts of this entangled state to determine whether X is a yes instance or not. And for the strongest possible notion of unclonability, we want to say that even this should not be allowed. And the second point is that the cloner A must be computationally bounded. So in particular, we'll say the cloner is a BQP or a quantum polynomial-time machine. That's because the cloner knows X. And if the cloner were not computationally bounded, the cloner could just make another copy of X. Because the prover who is not computationally bounded, after seeing X, produces X, psi X. So if the cloner were not computationally bounded, the cloner could just do whatever the prover was doing and produce another copy of psi x. So it makes sense in this setting for the cloner A to be computationally bounded. And also the verifiers B and C are naturally computationally bounded because verifiers are always computationally bounded in the proofs or advice setting. And I often average case unclonability is considered. Like it was done in this two works. So they considered that for each input length, the cloner must not succeed on average for cloning the proofs for that input length. But we don't have to do this, and we could also consider worst case unclonability as we'll do in our definition later.
Srijita, sorry, one small potentially stupid question in the previous slide. So do we need to have? Okay, can you flash the previous slide? I have fish on there.
Oh.
So this compute that do we have to also assume that A is computationally bounded in the advice case, or is it only for the proof case?
Also in the advice case, yeah. Also because the cloner was not computationally bounded. The cloner does know the input length.
Right, and they can produce two copies of the whatever advice you were trying to do. Yeah. Sorry, thank you. Yeah.
Sorry, I also have like a question here. I didn't quite get how. What does it mean that the cloner actually knows X? I mean, if the cloner knows X, then like can I just produce just send X to B and C? I was assuming that the unclonability must come from the hardness of A to recover X given psi X.
Yeah, as in X, B and C anyway know X because that's their input.
Yeah, I agree. But then you're also saying that the cloner A knows X in this setting. I didn't get.
As in, you could give the cloner X or you could not give the cloner X. Giving the cloner X makes your definition of unclonability stronger. And for us, since we considered a class which only has unclonable proofs, we have to give the cloner X anyway because there could exist a family of proofs which just write down X as part of the proof. So yeah, we should assume that the cloner always has access to X.
Yeah, I guess like the part I'm getting slightly confused is that if the cloner knows the secret, which is this classical piece of information X, then
it's not secret.
Okay, then maybe this part I misunderstood.
Yeah, so given as in there is it's a fixed state. It's not hidden from the cloner in some sense what the state is, because given X, you can assume if it's unique QMA that there isn't always a fixed quantum proof state. But suppose there is a unique proof state, then there is a mapping from X to psi X. But the point is the mapping cannot be done in quantum polynomial time. And if the cloner is computationally bounded, the cloner cannot just produce another copy of psi X.
Oh, so you are saying
the cloner cannot produce a single copy of psi X in polynomial time. And here we are requiring that the cloner given one copy of psi X should not be able to produce two copies.
So you are saying that implicitly the hardness of the cloner comes from the assumption that it is hard to produce the states psi X given X.
Yeah.
Okay, I see.
So, I mean, it's possible that even if it's hard to produce one copy of psi X given X, it might be easy to produce two copies of psi X given X and one copy of psi X. But here that is not the case.
Okay, I see. Thank you.
Okay, so now we'll define the classes which only have unclonable quantum proofs or advice. We'll call these strictly unclonable classes. So the requirement is that any candidate family of proofs or advice for these classes must be unclonable. Now, can we say that any candidate family of proofs and advice must satisfy the definition of unclonability from the previous slides? Like for any candidate family of proofs or advice, the cloner cannot distribute it between two different verifiers B and C. Unfortunately, we cannot do this. And the reason is why The reason why is suppose you have some canonical family of proof states, psi x, that works for a single verifier. Another possible family of proof states is just 2 copies of the state psi x. And if you consider this family of proof states, then the cloner doesn't even have to do anything to distribute it between 2 verifiers. The cloner just gives 1 copy each to each of the verifiers, and they can just solve the problem. But we observed that any polynomial-sized family of proofs or advice can only have polynomially many copies of a canonical proof. So something we could hope for is, suppose for any canonical, we could hope for that for any polynomial-sized family of proofs there exists some polynomial k such that no cloning operation can make a proof that is jointly usable by k verifiers. And this definition turns out to be viable, and this is in fact what we'll do. This definition, in fact, is also non-trivial because classical proofs are not unclonable in this way. For a classical proof, for all k, there exists a cloning operation that makes a classical proof usable by k verifiers. Whereas the definition we are going for is that there exists some case such that no cloning operation should be able to make the proof jointly usable by k verifiers.
Srijita, I think I got a little bit lost. Sorry. Yeah, sorry. Okay. This is going to be a little bit dumb, but let me straighten it out in my head. So when you say for any polynomial-sized family of proofs, I have. Okay, so let me just say the construction, which I think is kind of wrong, but maybe clarify why I'm getting confused. So I was thinking that a construction like the one you mentioned above, that if you have psi sub x, that's one family, psi sub x tensor 2 is another family. So if I have a polynomial-sized family of proofs, psi sub x, then I could produce another polynomial-sized family, right, which would just be psi sub x tensor k. Yeah. And then clearly it would be jointly usable by k verifiers. So I'm guessing you're using some notion of polynomial-sized family of proof, like the polynomial doesn't change.
Oh no, the polynomial depends on the size of the proof.
Right. So you're saying for every family there would be some polynomial size, but I cannot, like, if I have, okay, that's what I thought. Okay.
Is it clear or so if you have,
maybe I misunderstood actually. Okay, explain it maybe and I'll see if I got it.
Okay, suppose the canonical proof is n qubits, and you're given and suppose the canonical proof is the only possible proof or something. Okay. In the sense that only possible proof in the sense that if a verifier solves the problem with some proof, then it has to be psi x or something, and it has to be n qubits. Suppose you have a kn qubit family of proofs, then you could say that, okay, I shouldn't use kn, sorry. Suppose you have some m times n family of proofs. If you take, just take k equal to m, k equal to m plus 1, then m plus 1 verifiers should not be able to solve the problem with this if the state psi x is unclonable. I mean, if the psi x has...
Say it again. Say it again. I think I got lost with the variable names.
So suppose you have a family of, suppose the canonical family of proofs is the only possible family of proofs. I don't want to clarify too much at this point. Now, suppose you have some candidate family of proofs that is mn qubits, and you take k equal to m plus 1. If your family of proofs is such that, given m copies, you're not able to produce m plus 1 copies, then with this value of k, it should not be usable by k verifiers.
Okay. So your claim is that there exists such a k for every n size thing, that there exists a k which is like a threshold beyond which you cannot make more copies.
Yeah.
Essentially. Yeah. Okay. Got it. Thank you.
the unclonability that we consider in this case is worst case instead of average case. And that is fine for us because we are doing complexity theory and everything can be done worst case. Okay, now I'll give a clearer definition of what strictly unclonable QMA is and also strictly unclonable FEQP by qpoly. So first of all, the strictly unclonable QMA, which I denote by SU-QMA, it should be a subset of QMA. So it should satisfy the usual requirements of QMA, that there should exist a family of proof states that are usable by one verifier. And also, for any candidate family of proof states that are, say, Pn qubits, there exists some K depending on Pn, such that if you input it to a cloner and the cloner distributes it between K verifiers, P1 to Pk, and the verifiers each try to determine whether X is a yes instance using their parts of the proof that are distributed by the verifier. The verifiers are not all jointly correct with high probability. And so we'll use the Oracle version of this. The Oracle version is very similar. So yeah, SU-QMA is defined with respect to an Oracle oath. So here basically everything depends on the Oracle. The proof states depend on the Oracle. The cloner has access to the Oracle and the verifiers also have access to the Oracle.
Srijita, sorry, I kind of missed that. So what is strictly unclonable?
By strict, I say strictly because it only has unclonable proofs.
Okay.
Yeah. I won't define the Oracle version of Oracle version of BQP by, the strictly unclonable version of BQP by qpoly, but let's define the relational exact version. So FEQP by SU-poly, which is our strictly unclonable version of FEQP by qpoly, is first of all a subset of FEQP by qpoly, so it should satisfy the usual requirements of that. And also for any candidate family of advice states, which are say Pn qubits, there should exist a K depending on Pn, such that if a cloner takes the Pn qubit proof advice state and distributes it between K verifiers, that not really called verifiers for advice, but let's call them verifiers for now. And each of the verifiers, they get potentially different inputs, x1 to xk, and they're trying to produce outputs y1 to yk, which are valid outputs for these inputs x1 to xk for each of them. They should not all be jointly correct with probability 1, because this is the exact case.
Srijita, just a follow-up to the strictly unclonable dumb question. So do we also define unclonable QMA, or is there a way to think about it?
Yeah, so this previous paper, this work I mentioned earlier, broadband.
Oh, that's unclonable already. Oh, okay. Got it.
Yeah, they define unclonable QMA, I guess. So yeah, you can define unclonable QMA potentially as a class that it has an unclonable proof, I guess. I don't think this definition is very interesting. Okay. Yeah, I mean, it is kind of interesting. But yeah, I mean, that is also a thing you can define.
So here, unclonability means the functionality of the state, right? I think when you say unclonable, you refer to as the functionality of the state, right?
Yeah.
To be cloned. In that spirit, you are saying unclonable, not the state.
Yeah. No.
Okay. Now I got it.
Okay. So fine.
Sorry, I had a small question.
Oh.
So the difference between unclonable and strictly unclonable is just the number of verifiers?
No, it's for unclonable QMA, which I haven't defined, but which is a thing you can define.
Okay.
You require that there exists a family of proofs that is such that given it cannot be made usable by two verifiers. But in strictly unclonable, we want to say that this should be true of any family of proofs. So you have to there exists a case such that it should not be usable by k-verifiers questions, because as I demonstrated with the example earlier, if you only do 2, it's not viable.
Okay, so right. Because there exists some proof which is like k and qubits long, which can potentially be used by like k-verifiers.
Yeah, there's always such. Yeah, for any given k, there exists a family of proofs that can be used by k-verifiers.
Right.
Yeah.
Great. Thank you.
Could you please go to slide 9 once?
Yeah. Yeah.
Yeah. Just 1 second.
You can ask again.
Yeah. You can continue now.
Oh, okay. Okay, now I'll talk about what our constructions are. So for strictly unclonable QMA, as I said, we use the Aaronson oracle problem, which I'll call quantum on. So the oracle problem here is you are given an oracle that is either the identity oracle, which is the no instance, or the reflection about a high random state. So identity minus 2 psi, where psi is a high random state. And we have to determine which of these is the case to distinguish the yes and no instances. So the canonical proof state for this, when you're given a yes instance, identity minus 2 psi, is just the state psi. The good news is that this is a high random state because we are taking a reflection about a high random state, and we know that high random states are unclonable. So that gives us some hope that we can prove that this problem is strictly unclonable QMA, because if your canonical proof state is not unclonable, there is definitely no hope of proving that your any family of proof states is unclonable.
Srijita, sorry, I kind of missed how you define a canonical proof. Oh, I think I've asked you this question before, but
it's not something then defining. I'm just saying, okay, when you say some problem is in QMA, you have some
proof in mind. Yeah. Okay.
Yeah, I mean it's not a.
So it doesn't have to be unique and things like this, right? Like you're just assuming there's someone that I picked that I love. Okay.
Yeah. Okay, and I'll also mention what the candidate construction is for not candidate construction for FEQP by ST poly. So this is based on the Aaronson, Buhrman and Kretschmer construction separation between FBQP by qpoly and FBQP by poly. So this is for a relational problem. It's actually for a family of relations indexed functions from 0, 1 to the n to 0, 1. And you can show that with probability 1 over the choice of this function, this family separates the two classes. So how the relation works is that the relation R of f indexed by a function f consists of pairs x, y, b. The tuple y, b is the answer. So this is x, y, b is in the relation if fy xor fy plus x is equal to b. So given an input x, you have to output y, b such that fy xor fy plus x is equal to b. And when I say y plus x here, I mean the bitwise XOR of the strings x and y. The canonical advice states for this problem are binary phase states, which I mentioned earlier. So you take a superposition over all x and you put the fx as a phase for the input x. And yeah, these states are unclonable, as I mentioned. So there is some hope that since the canonical proof state is unclonable, we could hope to show that all possible family of proof states are unclonable. All since the canonical advice state is unclonable, we could hope to show that all possible advice states are unclonable. So I'll talk about what our general proof strategy is. The first part of our proof strategy is to show like a sort of rigidity result for the proof or advice state. Here I'm borrowing the word rigidity from the literature on non-local games, but I'm writing it within quotes because it's a much weaker notion of rigidity than that. So what we'll show is if the verifiers B1 to BK can jointly solve the problem, the QMA problem or the BQP by qpoly problem or whatever, given some proof or advice state by A, they can also jointly prepare a state that is something like psi to the k, where psi to the k is the where psi is the canonical proof or advice state. What this means is, as in the example of this for our SUQMA oracle construction is, if B1 to BK, the verifiers can distinguish between the two oracles, identity minus 2 psi psi and identity, with some joint state between them. They can also jointly prepare, perhaps with some more queries to the oracle, the state psi to the k. Yeah, so I mean rigidity in this sort of sense. So if there exists, yeah.
Sorry,
Yes.
go ahead.
No, I mean you can. I wasn't going to say anything important.
Oh, I was just making sure I'm following. So you're saying that somehow, obviously, if I have k many copies of psi, then B1 to BK can solve the problem. And you're saying that it's essentially rigid in the sense that the converse is also roughly true, that if they manage to solve the problem, they can produce the problem.
So it's not that if they manage to solve the problem, they should have started with the state psi to the k. But if they manage to solve the problem, they can end up with a state.
So you can extract efficiently the psi tensor k. Given like black box access to B1 to BK, you can construct an extractor or something.
Yeah,
is that
kind
the
of.
idea?
Yeah. As in, basically, if there exists these efficient verifiers that can distinguish the state, there also exist efficient algorithms that can produce the state psi to the k.
Good, sure.
Okay, and the second step of the proof is going to be to use the unclonability of the canonical proof or advice states. Now there is a catch here. Unclonability results usually say that you can't produce psi to the k starting from psi to the k minus 1, not starting from like arbitrary states with a few qubits. So we can't use unclonability results directly necessarily. We have to use some generalizations. And we'll see an example of how we do this later. So I'll talk about the proof of the hidden matching problem being an FEQP by SUPoly in more detail, because I think that's the more interesting proof. So let's first see how the FEQP by qpoly versus FBQP by poly separation works. This separation is essentially a separation between quantum and classical one-way communication complexity. So I'll talk about what the one-way communication complexity model is. So in one-way communication complexity, you have a known two-party function or relation in this case, defined on two sets of inputs. So you have two spatially separate parties, Alice and Bob. Alice gets an input Z1 from some set, also Z1, and Bob gets an input Z2. And they jointly want to compute a relation on Z1, Z2. And how they'll do this is Alice will send a classical or quantum message to Bob, depending on Z1. And depending on Alice's message and his own input, Bob will do something and produce some answer that is hopefully in the relation. And the measure of complexity we care about in this case is how many bits or qubits need to be communicated in order for Alice and Bob to compute this relation. An example of this, and the example we'll be talking about, is the hidden matching problem. here Alice gets as input a function from 0, 1 to then to 0, 1, and Bob gets has his input some string x in 0, 1 to then, and yeah, Bob's goal is to output y comma fy plus fy plus x for any possible y in 0, 1 to the n. Yeah, I already explained what the relation is earlier, and it was shown by I think Bar Yosef, Jairam, and Karanidis that this relation separates one-way quantum and classical communication complexity. So the one-way randomized communication complexity of this is omega 2 to the n by 2, whereas the exact quantum communication complexity of this is n. And the quantum state in particular that helps us achieve the n quantum communication complexity is this binary phase state. So yeah, I mean, given f, you prepare a superposition for all x and you give fx in the phase. So now I said I'm going to, the first step of our proof is going to be proving a rigidity result. So what do we mean by this in the hidden matching case? So we prove this theorem. So suppose for Alice's input f and Bob's input x, Bob state just before he does the final measurement to before outputting. Suppose the state is phi x comma f. We show that phi x comma f must be of this form, superposition over some coefficients alpha fx that depend on f and x. Basically, you take y plus, you get, you know, the relevant quantity fy plus x. You put this in the phase, as in the relative phase between y and y plus x is this relevant number, and yeah, the amplitude of the state is alpha f comma x, and this alpha f comma x is some amplitude, but the point is that if you take the square of this, the distribution is such that it has high mean entropy. It has omega n mean entropy, and it has omega n mean entropy with high probability over f and x. You can't show this for every f and x, but you can show this for like a constant fraction of f and x. So the canonical message state is in this family. In particular, in the canonical message state, each alpha f comma x is 1 by 2 to the n by 2. So even the canonical proof states definitely satisfy this, but we can show that any family of proof states must satisfy this. But like this is also rigidity in a very loose sense, because this is a pretty large family of proofs. We're not showing that the any family of proof states has to be exactly, I mean, alpha fx exactly has to be 2 to the n by 2 or so, 1 by 2 to the n by 2. But we can show that it is high mean entropy. So I've stated this result as such for exact protocols. For exact protocols, the state has to look exactly like this. But if this result also actually works for bounded error protocols, there will be a small error. So at this point in the proof, we're still fine with bounded error protocols. And the key idea of this proof is that when Bob's input is small, so remember in hidden matching, Alice's input is a function and Bob's input is a string. Let me just, yeah. So Alice's input length here is 2 to the n, and Bob's input length here is n. And the classical, quantum message from Alice to Bob is also n qubits. So in particular for this problem, if Bob were allowed to communicate to Alice, then the communication complexity would also be n. The catch here is that only Alice is allowed to communicate to Bob.
So, Srijita, sorry, I have a dumb question. So the function f is how is it given? Can you show the slide? Sorry, I just forgot to slide it.
Yeah.
So here the function f that's given to Alice, is it an oracle that's given to Alice, or
No, Alice is just given the entire truth table of the function.
but so we're not worried about efficiency things here?
No,
because
in
it's
communication
the communication
complexity,
complexity, they're unbounded occur.
Yeah. Yeah.
Okay. Thank you.
Yeah, I guess in when you go from one-way communication complexity to like advice, you should think of Alice here as the entity that's providing the advice, and the entity that's providing the advice does not have to be efficient.
The input instance. Yeah, okay, that makes sense. Not, thank you.
Yeah. So we have this result, and yeah, I'll just state briefly what the idea behind proving this result is. So Aaronson has a result that says when Bob's input is small, quantum one-way communication cannot have much of an advantage over randomized one-way communication for Boolean functions in particular. So only for Boolean functions, suppose if Bob's input is small, so suppose for hidden matching, we somehow defined a decision version of it. So in the normal hidden matching problem, it's a relational problem, but Bob's input is small. If we try to define a decision problem which had like this type of parameters, then it actually cannot have a separation between quantum and classical one-way communication complexity. Because Aaronson showed that for such problems, when Bob's input is small and it is a Boolean function, then if there is a quantum one-way communication protocol, there is also a randomized one-way communication protocol, actually a deterministic one-way communication protocol that simulates the quantum one-way communication protocol. And the idea we use here is that unless Bob's output has high mean entropy, this Aaronson protocol, for which only works for Boolean functions, but we can somehow convert from relational problems which have higher small mean entropy to Boolean functions. So we show that unless Bob's output has high mean entropy, the Aaronson protocol can be used to give an efficient randomized protocol for hidden matching, which is a contradiction because this due to Bar-Yosef, Jairam, Kernidis, there is a randomized lower bound for hidden matching.
So having low min entropy, does it like mean that you can find answers to the relation bit by bit somehow? Is that the
Exactly. Yeah. So the previous result is for a single verifier because it's one-way communication complexity with a single sender and a single receiver Bob. But we want to say things for K verifiers in our case. So we consider a more generalized setting of one-way communication complexity, which we call K receiver one-way communication complexity. I don't think the setting has ever been considered before, but it's the natural analog for us. So the joint advice that we'll give to the verifiers V1 to Vk will naturally correspond to the setting. So the setting here will be like this. We still have a single Alice who I'll just talk about hidden matching specifically here. The single Alice will still get F as her input, but now we'll have K Bobs who will each get different inputs x1 to xk. And Alice will send some joint message to all the Bobs. In the quantum case, the message can be entangled between the different Bobs. And depending on each of their inputs, the Bobs will perform some measurement on their parts of the input and try to give a valid output for the relation for Alice's input. So in this setting, ideally, we want to say that the state right before their measurements is like a tensor product of the type of states that we show one Bob had to have before their measurement in the single receiver case. Unfortunately, this is too strong and we can't show this. So we can't show that the Bob's states have to be in tensor product and the tensor product factors have to be exactly the states in the one receiver case. But what we can show that is that the distribution of the joint outputs of each of the K bobs has to have high min entropy. In particular, the min entropy must scale with K. So in the single receiver setting, the min entropy of a single bob was omega n, and we can show that for K bobs, the min entropy has to be omega n nk with high probability. Unfortunately, this result needs all the bobs to have zero error because we can't account for errors of all of them together. And it also needs parallel repeated hidden matching instead of just hidden matching itself. So we just take n copies of hidden matching. Technically, that should have given us entropy n squared or something for a single bob, but that doesn't happen. So for K bobs, we still get min entropy omega nk in this setting. Now, finally, so this is our rigidity result for K bobs. Yeah.
So before you move on, so when you say, but we can't show this, does it mean that the statement is false? Or does it just mean that your proofs don't apply to be able to show them?
Yeah, I don't know if it's false.
I see.
But yeah. I mean, it's probably not false, but yeah, we are not able to show this.
Yes, please.
So our final rigidity result is just going to be this min entropy result for the bob's outputs. Now, how do we use this rigidity result? So using this rigidity result, we can show that there exists some fixed x1 to xk such that with high probability over, so suppose you take two uniformly random functions, f and f prime, then you can show that with high probability over this choice of f and f prime, the states phi f x1 to xk and phi f prime x1 to xk must have small inner product with each other. By small here, I mean 2 to the minus omega k. Now, why is this true? I can give some intuition for why this is true. So think of the canonical proof states for, okay, I didn't write anything down for this, but think of the canonical proof states for a single copy of hidden matching. So if you think about it, if you consider two different functions, f and f prime, and you take the inner product between these two states with the canonical proof state, what this gives is just the inner product between f and f prime if you consider them functions from functions on say plus minus 1, or inner product between minus 1 to the fk and minus 1 to the fx and minus 1 to the f prime x. So for two uniformly random functions f and f prime, you should expect that this inner product is false because basically two random functions don't overlap on a lot of instances. So this is true for one verifier, and basically if you continue this, I mean if the proof states for the k bobs was like tensor product, then you should expect that the inner product will go down exponentially in k. So we don't have like we don't have that they're exactly tensor product, but still with the high min entropy statement, we can show a result like this. Now, why is this useful? So first of all, so these two states, phi f x1 to xk and phi f prime x1 to xk are obtained from the states that are given to the given by Bob by applying some unitary that depends on x1 to xk by the different bobs, but not on f. So therefore, it means that the inner product between the state psi f and psi f prime that were given by Alice must also be small. Due to this, we can use this result, which is basically the converse of the Johnson-Lindenstrauss theorem. It says if you have some 2n qubit, 2 to the n b qubit states, hx, that satisfy that all of their pairwise inner products for different x and y are at most epsilon, then b must be at least omega log of n by epsilon square. So you have some lower bound on the number of qubits that these states hx must have, such that all of the pairwise inner products are small. And we can use this result now to get a contradiction, because we have shown that the proof states that Alice sends to the bobs must have small inner product with high probability over the choice of f and f prime. But remember that we are getting k as a function of the size of the proof states to begin with. So if you take k to be big enough, depending on the initial size of the proof states, you can get a contradiction by using this theorem. Sorry, I know the last part was a bit technical, but yeah, that's the high-level idea. Okay,
wait, so what is the contradiction? Sorry. Can you go back? So I was with you until the. Where is the? We should be there. We should be large. And now, so please, Srijita, can you summarize the argument once, please? Sorry, I got a little bit lost.
So okay, so I'll just talk about this last point. It doesn't matter how we got here exactly. So we can show that with high probability over. Yeah, so with high probability over f and f prime, these states that Alice sends to Bob to the bobs must have small inner product with high probability. Okay.
Right.
So therefore with high probability, I mean, this is with high probability over f and f prime. So in particular, you can show that there exists a large number of functions such that for every different f and f prime from this large set of functions, the pairwise inner product between psi f and psi f prime is small. Okay. Now, if you take k to be such that
so k is the number of bobs, right?
Yeah, k is the number of bobs, and 2 to the minus omega k is the inner product.
Right.
So if you take k to be such that so Pn is, suppose the initial number of qubits in the proof states is Pn. Okay. If you take k to be large enough such that this lower bound omega log, instead of n here, you fill in the number of functions you have, and instead of omega square, you fill in 2 to the minus omega k. Sorry, instead of epsilon square, you fill in 2 to the minus omega k.
Right.
Now, if you take k large enough such that this lower bound you get on the number of qubits is larger than Pn, you get a contradiction.
Okay, thank you. Yeah, I think I have to think about it by myself, but I at least understand basically.
Sorry, 2 to the b should be larger than the number of should be larger than Pn, right? Or is it just b that should be?
Pn is the number of qubits in the original state.
Yeah, so,
and
okay. Pn is the number of qubits itself, right? Sorry.
Yeah.
Okay.
Okay. Yeah. So yeah, this is a bit brief, but this is the high level idea of the proof. Okay. Now I'll stop talking about technical stuff, but I'll talk about some other consequences of our results. So we know there are we have this class QMA, and QCMA is a subset of it. So we define this class strictly unclonable QMA, and it must lie in QMA minus QCMA, because yeah, if a proof is strictly unclonable, it obviously if a language is strictly unclonable, it obviously cannot have any classical proof. But there is also this larger class called cloneableQMA, which consists of QMA problems that have clonable proofs. It's potentially larger than QCMA because there can exist problems which have quantum proofs, but the quantum proofs are clonable. In particular, Nehoran and Zhandry in 2023, they showed that with respect to a quantum oracle, you can also separate the class clonable QMA and QCMA. Now we showed that there exists a problem in SUQMA. SUQMA by definition must lie in QMA minus clonable QMA because yeah, I mean, we said that if a problem lies in SUQMA, it cannot be in QCMA, but in fact, you can make a stronger version of that statement. If a problem lies in SUQMA, it cannot lie in clonable QMA, because if it lies in clonable QMA, it has a clonable proof, and if you're in SUQMA, you cannot have any clonable proof. So a consequence of our result is that with respect to a quantum oracle, you can also separate QMA and clonable QMA. So yeah, or with respect to a quantum oracles, at least of all these classes, QMA, clonable QMA, and QCMA are distinct. So okay, I'll talk about some open problems. So the first question is obviously whether you can show that there exist problems in SUQMA and BQP by SUPoly with respect to a classical oracle. So as I said, this is strictly harder than separating QMA and QCMA with respect to a classical oracle, and we don't know how to do that either. But there have been some recent developments in separating QMA and QCMA with respect to a classical oracle. So maybe with those developments, if we are able to show a QMA versus QMA full classical oracle separation, we can also show that with respect to a classical oracle, there exists a problem in SUQMA. And the second question is, can we show that there exists a problem in the strictly unclonable version of FBQP by qpoly instead of FEQP by qpoly? So as in we allow bounded error instead of exact quantum computation in that case. The problem here is that it's unclear how to even define this class because BQP by qpoly has error reduction, but relational problems in general don't have error reduction. Because yeah, I mean, unless you're always outputting the same result for a relational problem, there is no clear way to define, no clear way to do error reduction. So due to this, basically, if you can't do things like, or rather, suppose you have a proof state that succeeds with bounded success probability for one verifier. If you give k copies of the proof for k verifiers, it will succeed with probability like exponentially small in k. And this success probability is small enough that it's not clear we can get any viable definition in this. But yeah, even with a potentially viable definition, probably further refinements of our techniques are needed, because yeah, our techniques really don't work for any error at all. Yeah, that brings me to the end of my talk. Yeah, thanks for listening, and yeah, I'm happy to take further questions.
Okay, so do you guys have any questions? I have one very silly question before you close, keeping the spirit of the talk so far. So I was wondering, did we cover the? So you explained the intuition for the advice case, right? The unclonable advice, strictly unclonable. Or is there? Would you want to say a few words on how you do it for the decision, like the proof version as well? Similar ideas work, or do you have to use a different problem? Or
so
did you say it and I just didn't follow?
No, I didn't say it. So our rigidity result here is this, the thing I wrote here. If you have k verifiers, they can that can distinguish between the two oracles. They can also jointly prepare k copies of the state. So Now, first of all, you can say that if you started with k minus copy of psi and you have access to the reflection oracle identity minus 2 psi psi, then with polynomial many queries, you cannot prepare the state psi to the k. This is due to Aaronson and Kretschmer. This is known. But the problem for us is we need to show that starting from an arbitrary state which has too few qubits, you cannot produce k copies of psi. So for this, what we do is we generalize Werner's result about the unclonability of our random states. So we can generalize Werner's result without oracles to say that if you start with an arbitrary state that depends on psi and has too few qubits, you cannot produce k copies of psi. And then
so it doesn't go through any communication complexity like ideas. No, it uses a different technique altogether.
Yeah.
Thanks.
Sorry, I also have like a very high level question. So can I essentially understand that I mean your result is starting from like this separation, let's say the one that like Kretschmer, Aaronson, and Buhrman had, and you basically link that to have like this stronger separation. So basically, can I think of it as also like some kind of like compiler that might potentially apply to like all and separations we have between, let's say, BQP/poly and BQP/qpoly, like in various settings? Because I mean, to me, like you applied it to like this specific problem that's starting from like this, you know, this communication complexity problem. But is your separation maybe also can be seen as a strictly stronger result that can be applied to like all the previous known separations?
There is only one known separation between FBQP by poly and FBQP by qpoly.
Yeah, I know, but I meant for instance, even with like if you restrict to like some oracle separations, right? Because I think you're also mentioning at the very beginning that there are like a few separations now, like in various settings. It wasn't just the Aaronson et al. Result. And I was just wondering if you think your results could also apply to like those other separations.
Not obviously. We'd have to do the proofs from scratch for those.
I see.
Yeah, we can only handle the Aaronson-Kukuba oracle for now. I mean, yeah, I mean, it's since you know it was the easiest quantum oracle to handle, we just chose to do that. I mean, but something might still be provable with other quantum oracles or the classical oracle candidates. I don't know.
Okay, thank you.
Okay, I do have more questions, but I'll ask you later because I think you're past the time. Thank you so much, and let's thank the speaker for this.
Thanks for having me.
Yeah, thank you a lot.